Okay, so today we're going to talk about something called escape velocity. So before I define what escape velocity is, I really just want you to think about a certain scenario that I've set up here on the board. Okay, so in this scenario, I'm standing on the surface of the Earth, and my plan is to jump into the air with some initial speed, and my goal in doing so is just to get really far away from the Earth. I just want to get away from the Earth for whatever reason. So I'm going to jump from the surface of the Earth into the air in order to do so. Okay, so normally what would happen if I jump at some human speed is, well, I would eventually be pulled back down to just land back on the surface of the Earth. Right? So I haven't jumped fast enough in order to escape Earth's gravitational influence. But it is possible, in theory, if I do jump fast enough, for me to escape Earth's gravitational influence, and that's what we're looking at today. Okay? So the question is, how fast would I have to jump into the air in order to eventually escape Earth's gravitational pull? Okay, so let's think about what that means for a second. If I want to escape Earth's gravitational pull, I need the force of gravity acting on me to go to zero. That way, Earth has no influence over me. Okay, so if we look at what the force of gravity is for a spherically symmetric object such as the Earth, well, it turns out it's equal to negative g capital M lowercase m over lowercase r squared, and it's in the radial direction, so r hat. And the force is negative, meaning it's an attractive force. So the force is directed along the negative radial direction. Okay, the direction is not what's important here. What's important is we want the magnitude of this force to go to zero. So what condition has to hold such that the magnitude of this force goes to zero? Well, as you can see, since the force is inversely proportional to r squared, I need r to go to infinity in order to escape. That's the condition that must hold. So in other words, I just need to get infinitely far away from the Earth, and then I've escaped its gravitational influence. Okay? So in order to answer this question, what the escape velocity is for the Earth, we're going to use conservation of energy. But before we go into that derivation, I want to outline some of the assumptions that go into it. The first one, really important, is that there's no friction in the system anywhere. So for example, as I jump into the air, I'm going to be in Earth's atmosphere, moving through it at some speed. And as we know, that's going to create a drag force that takes energy away from the system. But we're going to ignore that. Okay, the second thing we're going to ignore is the recoil of the Earth. Now, as I jump from the surface of the Earth will recoil some small amount in the other direction, but since the Earth is so much more massive compared to me, I can just ignore that altogether. It doesn't really matter in this context. Okay, and the last thing is, there's no propelling force that acts on me. So in other words, I'm not jumping into the air with a rocket attached to my back, I'm just jumping into the air. And after I've left the surface of the Earth, the only thing that is, the only force that's acting on me is the force of gravity. That's it. Okay, so now to derive the escape velocity equation using conservation of energy. Okay, so since we're applying the concept of conservation of energy, we really have to just define what the system is first. And the system we're considering here just consists of two parts. It's me and the Earth and nothing else. So we're just going to imagine those are the only two things in the universe and ignore everything else. Okay, so the total energy of this system consists of two terms. One of them is a kinetic energy term, describes how fast things in the system are moving, and the other is a potential energy term, describes how things in the system are interacting with each other. Okay? So, since the only thing in this system that's moving is me, there's just one kinetic energy term. It's equal to 1/2 lowercase m v squared. So in this case, lowercase m is my mass, v is my speed. That's the kinetic energy term. And the potential energy term is negative g capital M lowercase m over lowercase r. And again, lowercase r is the distance between me and the center of the Earth. Okay? So it's not the distance between me and the surface of the Earth, it's the distance between me and the center of the Earth. That's an important thing to know. Okay. So we have both of these terms. When you add them together, you get the total energy of the system. Now, an important thing to note is that energy is conserved in this system. Okay? So I can look at the energy at any moment in time, and I will come up with the same result. And this is because there are no external forces, okay, external to me and the Earth that is, that are acting on the system, taking energy away or putting energy in. Okay? So what we're going to do here is think about an initial state of the system, which is right after I jump off the surface of the Earth. So just as my feet leave the ground. Okay, well, my distance from the center of the Earth is equal to the radius of the Earth at that time, right? So lowercase r is equal to capital R. Now, in this initial state, the kinetic energy is 1/2 mv0 squared, okay? So that is my initial speed again. And the potential energy is negative g capital M lowercase m over capital R, the radius of the Earth. Okay, so we can write out what the total energy is. It's just the sum of these two terms. We can also look at what the total energy is in the final state. Now, the final state here is when I do get infinitely far away from the Earth, when r goes to infinity. Okay, so we can see here that the potential energy term goes to 0, right? Because the potential energy term is inversely proportional to that distance. So if the distance gets infinite, then the potential energy goes to 0. That's just the way the potential energy is defined. Okay, now, in the final state, let's look at what my kinetic energy could possibly be. Well, it could be 0, meaning now I have 0 speed relative to the surface of the Earth, or it can be something positive, but it cannot be something negative, right? So, in other words, in order to escape, when I add these two up, I'm going to get something that's greater than or equal to 0. So my total energy, the total energy of the system that is positive in order for me to escape. The total energy needs to be positive in order for me to escape, and if it's anything negative, anything less than 0, then I'm bound to the surface of the Earth and I can't escape. Okay? So that's the condition that has to hold. Okay, so now let's apply that using everything we just wrote down on the board here. So the total energy of the system in the initial state is 1/2 mv0 squared minus g capital M lowercase m over r. Well, that total energy has to be greater than or equal to 0. So it sets up this inequality here. Now, when we take this inequality and we solve for v0, we get that v0 has to be greater than or equal to the square root of 2 capital G capital M over capital R. Okay? So any speed that exceeds that is fine, you'll escape. If you're right on the cutoff where v0 equals the right-hand side of the equation, that's called the escape velocity. So it's the absolute minimum speed you need in order to escape Earth's gravity. Okay? So that's what the escape velocity means, and that's how to derive. Now, you can have a little bit of fun with this escape velocity equation by thinking about black holes. So, as you know, a black hole is an object that's got such an immense gravitational influence on things that not even light can escape from it. So, in a sense, you can just define a black hole by its escape velocity. We can set the escape velocity equal to c, the speed of light, where the speed of light is 3 times 10 to the 8 meters per second. And we can see what happens when we do that. Okay, so right here, I've taken the escape velocity equation and set the escape velocity equal to c. Now, as you notice, there's some radius term in here. So what does that radius mean? We'll get to that in a second. Let's solve for it first, okay? The radius is equal to 2 capital G capital M over c squared. Okay, it turns out this is called the Schwarzschild radius. What does the Schwarzschild radius mean? Well, it's the radius you would have to crush an object down into in order to turn that object into a black hole. So let's imagine how that would go. So I'm going to start off with some spherical object. It has some normal radius. It's not at the Schwarzschild radius yet. But what we're going to do is crush it down by applying force from every side. We're going to crush this object down smaller and smaller, but while doing so, we're going to retain all the mass. Okay? So none of the mass is leaving, but it's getting smaller and smaller, more dense. Okay, once we get to the Schwarzschild radius, we've created a black hole. The reason for that is the escape velocity from this object now is the speed of light. So you've just created a black hole. Okay, so let's get some sense of what the Schwarzschild radius for everyday objects might be. Let's think about, for example, me. I'm 80 kilograms, that's my mass. So what is my Schwarzschild radius? In other words, what size would you have to crush me down into in order to turn me into a black hole? Well, we can use the equation for the Schwarzschild radius, which gives us 2 times the universal gravitational constant, g, times my mass divided by c squared. Okay, when you crunch these numbers, what you get is 10 to the minus 25 meters. That's an incredibly small size. Okay, so to give you some perspective on this, a typical atom is about 10 to the minus 10 meters in radius. So you're crushing me down to a size that's 15 orders of magnitude smaller than the size of your typical atom. That's what you would have to do in order to turn me into a black hole. So that sounds kind of outlandish. What could ever happen in nature that would produce a black hole? What's the mechanism that would lead to the formation of a black hole? Well, it turns out this does happen in nature, and the process that leads to the formation of a black hole is the collapse of a dying star. Now, as a star goes through its lifetime, there's a balance of pressures that occurs. Okay, so there's nuclear fusion going on in the core that creates immense pressures that push outwards. These pressures try to make the star expand or blow up. But there's also gravitational force, which tries to make the star collapse in on itself. And there's a balance between those two. Okay, now, as the fuel in the core is depleted from the star runs out of fuel for nuclear fusion, this outward pressure is lost, and gravity takes over, causing the star to collapse in on itself. Now, when this happens in the most massive stars, this collapse just goes on forever. There's no force in the universe that's strong enough to oppose it. And if this collapse happens without end, not only will the star collapse into its own Schwarzschild radius, but it will keep collapsing past that until it collapses into a point of no size, called a singularity. So all the mass of that star is contained within a point with no size. And around that singularity, you have what's called the event horizon. Meaning, if you crossed into the event horizon, you're done. The escape velocity is c, or greater, right? So you can't escape once you've crossed into the event horizon. And it turns out, the event horizon has a radius which is equal to the Schwarzschild radius. Okay? And that's what a black hole is.